There we go. All right. So let's talk about free radicals. Now, this is an entirely different thing than what you have done so far. It's going to be all completely new, but there will be some things that are also old, okay, that you have already done. So that should be good. That's always nice to kind of build on that foundation that you already have. So let's talk just a little bit about the intermediates so far. And I'm talking about the carbon intermediates, of course. All right. So, of course, carbocation. Oh my God, we have done so much of carbocation. So, carbocation probably as your best friend or nightmare. And then we've also done carbon anion. And you may not realize it, but this was actually part of the C triple bond C, that one, right? So that's an anion. So you have done this one. The one that I have not done with you is carbene. Okay, this was carbene. And we learned about it, but I told you to skip that reaction in alkenes, and I'm still going to skip it. Okay, so we don't need to do this. But now what we're talking about is going to be carbon with a single electron. Okay, and that's a radical. So let me just write a couple properties that we've talked about before for radicals. So it has a single electron, and then it is also electrically neutral. So that electron that you have does not cause it to be negative. For it to be negative, you have to actually have a negative charge, which means you need to have 2 electrons, okay? Even though carbene has 2 electrons, and yet it is still not negative. So it's kind of weird how these carbon intermediates work, okay? And that's why we study them, right? Because they're so interesting and they have such different properties. So that's a radical. Now, you have not seen a radical yet, okay? We have not. I have not covered it anywhere at all, and you've not done anything with this, okay? So it's all new to you, so feel free to ask questions. Stop me wherever you want, okay? So first of all, let's talk about formation of radicals. Formation of radicals happen, if you remember, from homolytic cleavage. So we talked about this like way before, like in chapter 6, when I was talking about the carbon intermediates. That's when I mentioned that you have 2 kinds of cleavages, a heterolytic cleavage and a homolytic. I'll write both of them. How is that? Okay. So this one here is the homolytic cleavage. So homolytic cleavage is when one electron goes to each of the atoms. Okay, so you have a bond, and that bond has 2 electrons, and when the bond breaks, each of the elements will take 1 electron. Okay, so you have a radical and then a radical. Now you can write 2 a radicals if you want to, that's up to you. And then the heterolytic cleavage, which we have been dealing with, is this one, right? So in this one, you have B, which is taking away all the electrons. So A is left without any electrons, and then B has the electrons. This is how you form the carbocations, right? So you had the bromine or the chlorine as the leaving group, and it left, and then you got A plus, okay, or C plus, okay, in there as your intermediate. So homolytic cleavage is really what we're talking about for radical formation. So which means that the homolytic cleavage is what we will be talking about also as we go forward, how that works, okay? But I will get to that also in a few minutes, but I'm going to talk about some other things also, which are a little bit easier to remember, okay? So we can get that out of the way. So first of all, I want to talk about stability of radicals. Now, you can have any kind of radical, by the way. You can have even a bromine radical, chlorine radical, hydrogen radical. You can have a large compound that is a radical, okay? So, I mean, anything is possible. Anything is possible with the radical reactions, okay? So when we talk about stability of radicals, we're actually dealing with just carbon right now. And that carbon radical is just like what you had with the carbocation. Okay, so which means you have something like this. So this would be like, if you had the T-butyl cation, but now you have a T-butyl radical. So it's a tertiary radical. So this one, and then you have the secondary radical. So CH3 and then CH3, and then here is the hydrogen. This is a secondary radical, and then which is more stable than a primary radical, which is more stable than a methyl radical. A methyl radical is also, I don't know if I even would call it primary radical. I don't think I want to call it that, but you know, there. So this is just like the carbocations, okay? So I want you to relate it to that so you don't have to memorize something completely new, okay, over here. So tertiary radicals, more stable than secondary, then more stable than primary radicals. That's how it works. Now, radicals also have resonance. And you remember we went over resonance when we were talking about carbocations also. And if you've forgotten, please go back and check on that, okay? So that was chapter 7 that we did, a huge, huge part. And then there was one part in it when I was talking about substrates, I was talking about resonance, okay, for cations. So I'm going to take the same kind of compound here, which is what we call the allyl radical. There I took the allyl cation. Okay, so what's the allyl radical? Remember, allyl is 1, 2, 3. It's a 3-carbon system where you have a double bond somewhere, either place, it doesn't matter. Now, in this case, I'm going to put the radical on this carbon. That's the allyl radical. So what happens in this resonance is one electron moves here. Now, in this case, I really want you to be careful when you draw your arrows. Make sure you draw half-headed arrows, okay? A full-headed arrow shows the transfer of 2 electrons. Half-headed arrow shows the transfer of 1 electron. And since we are talking only about 1 electron in radical reactions, everything is going to be a half-headed arrow. Okay, so this is something you kind of have to adapt, okay, for this chapter. Okay, so you move 1 electron here. In this double bond, you're going to move 1 electron here and 1 electron on this carbon. So I know it seems like a lot of arrow and it kind of seems funky, but you know, that's how it is. That's how radicals are. And so now what happens is that this one here will create the double bond, and this single one arrow that we had here will create the radical. And if you remember, the allyl cation was the same way. If we had the cation, we'd just be moving 2 electrons. And so we will have something like this, okay? Except in this case, we're just moving a radical. So we're just moving a single electron. And so when you move single, the arrows look a little bit different, okay? But this would be for the allyl cation. Oops, my writing is really fantastic today. Okay. Okay. So the other thing I want to remind you of is that an allyl cation will be even, or radical will be even more stable than a tertiary. So whenever you have resonance, that kind of a radical, and we did that in cations also, even the cation which has resonance is more stable than a tertiary radical or a cation, okay? So there's a lot of similarities there, okay? So that kind of helps a little bit. Now, if you want to practice a little bit for drawing resonance structures, here is a good one, okay? So you can try this one. I'll write a few of them, and then you can practice more for yourself. It will work just like you would have a cation. So let's say you have a radical here. The only thing about radical is you have to draw half-headed arrows, okay? And in some cases, you have to draw 2 arrows. Now, the resonance arrow does not change, okay? That's still the same. But as far as this arrow is concerned, see, here is you have the radical. This arrow goes here. This arrow goes here and here. You know, so you have to draw so many arrows in this case. Now, if you don't draw this one, it's okay. All right, this one you can forget if you don't want to draw that, okay? And I'll skip that in the next one. Okay, so now what you have is you still have the ring, you have the double bond here. This double bond has not changed yet, its location. Now this double bond has moved and the radical has shifted over here. So now I'm going to write the next one, and I'll see how I can save you one arrow. And so in this case, we'll move this here, and we'll move this on the carbon. Remember to write the arrow pointing towards the carbon. Sometimes you will see that when I grade your work, I'm pointing those things out because it matters a lot. Your bonding matters a lot. Your arrows matter a lot, okay, to me. So make sure you draw them correctly, all right? So once you remove that, then you will have, this is still the same, this is still the same. Now this double bond is going to be here and a radical is here, and I will leave the last structure to you, okay, to finish off. So if you want to take a minute and write that out, you can do that. I will pause. All right, I hope you have it. And that's resonance, okay? And you can't forget resonance, okay? So you have to keep writing resonance structures all the time. All right, so now let's look at something which is a very typical kind of a question, okay? So here, let's take a compound that has all sorts of carbons on it, okay? So this one has primary, secondary, tertiary, secondary, did I say secondary already? And then a double bond also, okay, on there. So you got all sorts of carbons on this structure, okay? So the question will be, which radical is going to be the most stable? And you will see this is a very typical question, okay? Just like I gave you the question for carbocation stability, this is also a very typical question. And just like you did not mess up the carbocation stability, please don't mess up this one either. So first, what we'll do is we'll just go ahead and write all the radical ions that are possible, okay? And I shouldn't say ions, I don't know, radical structures, okay, that are possible. So we'll start, and you can draw the structures as fast as you can if you want. So this is what we're doing here. We have this, we have that, okay? And if you're wondering, how do I know there's going to be a radical there? Well, just the way you form carbocations, you never had a quaternary carbocation, so don't draw a quaternary radical, okay? You had a tertiary, secondary, and primary and all that, all right? So which means that this is possible. The next one possible will be this one. You cannot have a radical on a quaternary carbon, okay? So this carbon is a quaternary carbon, all right? So you cannot have a radical there. Okay, so that's another one. And then let me draw another one. And right, that one. There's a radical here. And then the other one is going to look similar because it's going to be also on the double bond right here. Now, we did not draw carbocations on double bonds. I will admit to that. Okay, I will admit we did not do that. We're doing it here. Okay, but we did not do it in carbocations. So that's something different. Okay, so now looking at all these four structures, so think of it like a multiple choice question. So if I were to ask you which is going to be the most stable radical, I am hoping that you are thinking this is going to be the most stable. And this is most stable for two reasons, okay? One reason is, of course, that you have a tertiary radical. That's one reason. The other reason is the resonance, because you have the double bond right there, okay? So that double bond is going to give it the allyl radical resonance that it needs to be stable, okay? So which means when you're trying to do any reaction on this kind of a compound, your major product is going to be this. Now, I haven't even told you what kind of products we get, okay? But we're getting there. Okay, so this is just a little bit about the stability of radicals. Questions, anything? Okay. So then let's talk a little bit about the kinds of reactions, okay, to expect in this chapter. And we do all sorts of reactions, okay, in this one. So we'll just write them all, and then I'll take it one by one. So the types of reaction is you will have substitution. So which means that if you start with something like propane, and you can see that I wrote the bromine on the secondary carbon. I did not write on the primary carbon, okay? Because now we've already talked about the stability. So this is the product we are talking about, okay? Now, I hope that when you look at this reaction, what should go through your mind right now is how is this substitution taking place, right? Because when we learned about substitution reactions, and oh my God, we spend so much time on substitution. So in that substitution, you need to have a leaving group. You have to have a nucleophile, right? And we spend so much time talking about the strength of the nucleophile and the nature of leaving group, the nature of substrate, and all of that kind of thing. And when you look at this kind of a substrate, you're thinking, oh my God, this is just an alkane. It's just an alkane. Doesn't mean it doesn't have a leaving group. Can anyone tell me what the leaving group is here? What's my leaving group? Okay, so the leaving group is hydrogen, and you don't have to think too much. You just have to see what's on this carbon, and this carbon now has only one hydrogen. Well, if it's only one hydrogen, obviously what is left is a hydrogen. Okay, so it's that simple. And then you put the minus on it and then make it a hydride. Okay, so took too long there. All right, so substitution reaction is one of the main reactions actually for free radical reactions. The other one is going to be just the addition reactions. So addition, we did all of that in alkene and alkynes. So that was addition reaction. So here, if you have a double bond and this is Br2, this is the addition reaction you get. And I really hope you're looking at this right now and you're thinking, is she crazy? You know, because an addition reaction should be happening on an alkene and she's not adding it on alkene. So this is actually not an addition reaction. So I should actually just cross that out. This is also a substitution reaction. Okay, so you are not crazy. I am crazy. There we go. Okay, so this is still a substitution reaction, but now the substitution is happening a little bit differently. Okay, this is called allylic substitution. The top one is the traditional substitution, and then this one is an allylic substitution. Okay, now I'm going to do addition reaction. I messed with your minds a little bit here. Okay, so now we're going to add HBr. And this HBr, if you see, and again, I hope you're thinking, what the heck is she doing? You know, like I messed up the other one. I didn't mess up this one though. But I hope you're thinking, what the heck is she doing? Because technically, when you have addition reactions, hydrogen should go to the carbon with more hydrogen. We should be following Markovnikov's rule. But here I'm not following Markovnikov's rule because this reaction is anti-Markovnikov. Okay, so that's the beauty of these reactions. And you can see this, like we have not done these reactions before. Okay, these are entirely a new set of reactions for us. None of this, you know, I mean, like we have done substitutions, but not this type, you know, of substitutions where hydride is a leaving group. We've never done that kind of a thing before. So it's all very new, okay, kind of a reaction. And the last reaction is also new. And this one we will not do a whole lot, okay? But I'm just going to write it there for you. But it's not really a reaction that we do a lot, okay? So this is 1, 2, 3 carbons, and this is also 1, 2, 3 carbon fragment. And I am taking 3 carbon. It doesn't have to be 3. It could be any fragment, okay? And if you want, you can change that. If you feel like, oh my God, this is confusing me, then go ahead, let's change that. You can just make it a cyclohexane ring. That's fine. Okay, so that way you will see how this reaction works. Okay, I mean, if I keep a chain and a chain, it's hard to see what's going on. So let's see in this one, what happens in coupling is when you just join two things together. Okay, so you still have the cyclohexane, but now you will form a new bond where the dash line is. Okay, so now here, so 1, 2, 3, so there's carbon, so which means this is a new bond that we have just formed, and that's called coupling. And this is something also that happens a lot. Okay, now of course, you know, since this is just the first semester of organic chemistry and you're learning some things, and even when you do the second semester of organic chemistry, it's not that you're going to become masters of organic chemistry. Nothing is, it's not going to happen. Okay, even for me, it's not going to happen. So even if I do a PhD in organic, which I do have, it doesn't happen. Okay, I don't know all chemistry, okay, and all organic chemistry, because this is so much to do. And the reason I'm saying this is because the last reaction I have written here, which is the coupling reaction, it's not a very common reaction that chemists will do in a lab. This kind of a reaction is very common in industries. Okay, so it's not common in the lab. So in industrial reactions, coupling happens a lot, and that's how you can actually make large alkanes, okay, if one needs to. So coupling reactions, you know, has its own niche, okay, sort of. There are people who just do these kind of reactions. So these are the 4 reactions we'll be talking about, okay? So the considerations that we have to have in all of these reactions that we're talking about is what bond is going to break, how is this going to happen. I mean, at this point, I haven't even told you how radicals are formed. The only thing I said to you at this point is that it's a homolytic cleavage or homolytic fission. Okay, that's it. It's just, you know, homolytic. That's it. I haven't said to you how it happens. Can it happen to everything? Or is it only for specific molecules? Okay, so that's the kind of thing that we need to talk about now, because now we're getting into reactions. So what bonds can break? Obviously, the ones that are weak. Okay, so how do you know what kind of a bond is weak? Well, for that, you have to look at bond energies. Okay, so there was a whole portion in chapter 6 that I did not do with you. Okay, and that part was the bond energy part. All right, so if you want to look, you can look, but you don't really have to. My PowerPoint is good enough. Okay, so if you just want to look through my PowerPoint to see the bond energies that I'm talking about, that's good enough. Okay, because I'm not going to be asking you to do any calculations, and neither am I going to ask you to you know, predict which bond is weaker than the other. I'm expecting you to know this, okay? Because I'm going to tell you now what's going to work for us, and just kind of remember that part, okay? That's how it's going to work. So what's not going to break? Okay, first of all, let me just tell you what you are not going to break. So, which means, what is a strong bond? A strong bond is a carbon-carbon bond. It doesn't break. Now, carbon double bond is a different thing. Okay, a pi bond is a little bit different thing, and it can break because you know, we do this all the time in the lab, and you probably saw that when you did your alkene lab, that, you know, when you add bromine, it adds on automatically really fast, you know, within seconds it will react. So the pi bond is easy to break, okay? But a carbon-carbon single bond, which is a sigma bond, it's hard to break, because what we are talking about is actually a bond cleavage, right? So when you form a radical, you have to break this bond. All right, and that's what we're talking about here. So we're not just talking about breaking a pi bond, we're talking about breaking a sigma bond, okay, over here. So this bond is not going to break, okay? What other bond is not going to break is a CH bond, okay? Never going to break. So what does that mean? It's never going to break. It will break. Of course it will break. We have to break it because that's what's happening in the substitution, right? The hydrogen is leaving, the hydride is leaving, so we have to break it. But I'm going to tell you what we mean by not going to break, okay? So the bonds that are easy to break, the bonds that are easy to break are going to be, for us, bromine and chlorine, some peroxides, so iodine. Fluorine is also actually pretty easy to break. Fluorine it's just unbelievable, okay? So all of these break. This one is very slow. That's all. Then you have peroxides that break. So this is hydrogen peroxide, okay, H2O2. So this bond is going to break. So there is a whole table in Klein that you can look at if you want to, but really honestly speaking, you should not waste your time on it, okay, too much. All right, so just focus on what I'm teaching you here, and that should be good enough, okay, for us. Okay, so when I'm saying, okay, what bond is going to break, what that means is I'm talking about the reaction itself, okay? How do you do this reaction? Because now I'm going to mention to you how this reactions works, because we haven't talked about how radicals are made yet, okay? So let's talk about the radical reaction mechanism. I'm taking you step by step, okay? It might seem that I'm taking a long time to get there, but I'm hoping that this will work for you, so that you understand this a little bit better, okay? And because it's a very different kind of reaction. It's nothing like what we have done before. When you do a radical reaction mechanism, it's not the same as any of those mechanisms we've done before, where you have a nucleophile and an electrophile. We don't have that, okay? So when we do a radical reaction mechanism, there are 3 steps that we need to take. One is called initiation. Then the other 2 that I'll write is propagation and termination. Okay, so there are 2 more steps coming. So there are 3 steps that we need to take. Okay, the first step is called initiation, which if you want, you can write I for that. Okay, so initiation is when you create radicals. Now, this is the big thing, and I've been talking about this, right? I haven't told you how to make radicals. Well, now I'm going to talk about it. So how do you create radicals? You need to provide energy. So this requires energy because you need energy to break bonds, okay? The bonds are not going to break by themselves, okay? So you need to have energy. Now, what is energy? What kind of energy are we talking about? There are 2 kinds of energies that we deal with. One is light energy and the other one is heat energy. So either of those 2, okay, will work for us. And then remember, of course, that only weak bonds are going to break. So how do you write an initiation? Okay, how do you write an initiation reaction? The way we write this is that here is your bromine. Then you give it heat. Heat is a triangle, remember delta. And then you write those 2 arrows showing the bond breaking. And now you have 2 bromine radicals. That's it. This is the initiation reaction. Now, if you're thinking, I don't see any carbon, you're absolutely right. That's because you cannot break a carbon-carbon bond, okay? So you cannot use that as your initiation step, okay? That will come in the next one, okay? But I want to give you one more example. So you can use any halogen. Don't use fluorine or iodine, okay? Don't use any of these, but chlorine and bromine is going to be fine. And the other one that you're going to use, or you can use, is peroxide. And now I'm going to use a different energy source just because to give you an example how it is written, okay? So H nu, if you remember Planck's equation, which you did way back in Gen Chem maybe. So Planck's equation is how to determine energy of a radiation. So where H is Planck's constant and nu is, this is nu, that is frequency. Okay, so you multiply the Planck's constant with the frequency of the radiation, and that is how much energy is given off. So light energy is a different kind of energy, a different amount of energy than ultraviolet, which is different than, X-rays, which is different than radio waves. So all have different amounts of energy, right? So like light energy will not hurt you, right? So, but if you have ultraviolet radiation, that can actually damage your skin and kill your cells and all that. So you have to be careful, right? So that is actually determined by Planck's equation. So instead of writing E is equal to H nu, we just write H nu. And when you write H nu, that means that you're actually exposing the reaction to light. And what does it mean? Does it mean you're just keeping it out in the sunlight? In some cases, you can do that. And actually, that's a big problem. And I'm going to talk about that at the end of the class, okay, of why light is a big thing over here. So at this point, I'm talking about like, a heavy duty lamp, okay? Like if you have lamps in your home, you know that they get really heated up, okay? And so You can use any of those kind of lamps or a lamp with a high wattage. Okay, that will work. And so again, that will cleave this. And so when you cleave this again, the reason I'm writing this bond is because I'm going to show you that that's the one that's breaking. So in this case, you get 2 hydroxide radicals. These are extremely common reactions, okay? We're just doing them really fast right now, really fast in the sense that we're doing only one chapter, but these reactions happen all the time. They happen in the atmosphere all the time. They happen in your body all the time. You may not even realize that. So I'm going to bring it to your attention, okay, when we finish this. Okay, so that's initiation. What is initiation again? Initiation is creating radicals. And this is the big thing, okay? If you need to box this, box it, okay? But this is the big thing. You have to create radicals in order for you to start doing the reaction, okay? As I said, this is not a nucleophile electrophile situation. This is a very different situation. So that was the first step, okay? Initiation. The second step is propagation. Propagation is when the reaction actually happens. This is where the main chemistry is actually happening. And then you form products. The main thing here is that products have radicals, which means we're still working in the radical situation. Okay, so all these 3 things, these are important. The reaction of, I shouldn't say the 3 things, the 2 things are important here, because propagation itself is just the reaction, okay, of radicals that's happening. So which means this is the step where you're going to be forming products, and then the products will also have radicals. Okay, so I'm going to write one step here for you right now. And that is if you take something like HCH3, so now HCH3 is just methane. So I'm taking methane and I'm showing you how this substitution is going to work. So now you have that radical. And this is not an electrophile nucleophile situation, as I said. This is a radical situation. And in this case, what happens is this bond is going to break. This is what happens. So what does this mean? It means that the carbon is breaking its bond. And actually, I should write it differently. Hold on 1 second. Let me write it a little bit differently because I have to form a radical here. There. Let me break it this way. Sorry about that. Here. This way. And here is the Br, which is going to form a bond with H. So you end up getting HBr, and then you end up getting CH3 radical. So this is the bond breakage that is happening. And I just said to you a few minutes ago that a CH bond does not break. But the CH bond actually does not break by itself. So like the initiation step that we did, I could not have initiated the reaction using methane. But once the reaction is started, then the radical is going to start reacting with anything. And that you cannot stop. Okay, that is something that's going to happen. All right, so now the CH bond can break. Now a CC bond can break also, but we generally don't break that, okay, because that one is still harder to break than a CH bond, okay? So generally in these kind of reactions, we will be breaking CH bond, not a CC bond, okay? So no fragmentation going on, only coupling going on, okay? No fragmentation. So I wrote all these reactions up here. All the substitutions and addition and coupling, these are the only ones. Nowhere did I write that any kind of carbon is fragmenting, okay? We're not doing any kind of fragmentation that way. Okay, so this is propagation, okay? So what is the big thing over here? The big thing here is actually not the reaction of radicals, but the big thing is that the products will have radicals. That's the big thing. So I said there were 3 steps. So the third step is termination. So we have initiation, propagation, termination. If you don't have three steps, you don't have a mechanism. Okay, so this mechanism a little bit more involved. You can see this, but it's very simple. Okay, don't make it more complicated. So what is termination? Termination is, of course, end of the reaction. That's it. We're done with it. So now in this case, the main thing is no radicals in the product. So how do we do this? Which means this is the reaction I'm talking about. So if you take Br, radical, radical, they're both going to react with each other. And in the end, you get the Br2 back, but there is no radical anymore. I don't know why I wrote that, but there's no radical anymore. Okay, so the right-hand side now, the products now have no radicals in them. In propagation, you can see they have radicals. Initiation, of course, the whole point of initiation is to make radicals. But here in termination, you do not have any radical. So you can do termination with literally anything. Okay, so I can take the CH3 radical also, treat that with a bromine radical, and I can get methyl bromide. So long I don't have any radicals in the product, I can combine any two things. And that is how coupling occurs, because you can take any two carbon radicals. So I could have taken a CH3 with a CH3 and then reacted them together to get ethane. That's it, so that's a coupling reaction. That can also happen in termination. Anything is possible. You can combine anything, provided you don't have radicals in the final product. Okay, so that's the main thing. So what you're going to box over here is no radicals in the product. That's the main thing here. So how do we stop a reaction? Does anybody want to take a guess at that? I know you can do it. Okay, so you can do termination in different kind of ways. Okay, the main thing about a termination is should not have any radicals. So sometimes what you need to do is add a terminator to the reaction, and a terminator, if you want a more specific term or a chemical term for it, is called a quencher. Okay, so you quench the reaction. So what the quencher will do is it will go around and eat up all of the free radicals. Okay, that's what it does. So you add that to your reaction, and then you can stop the reaction from happening. Okay, so that's termination. So any kind of a reaction is going to have three steps. So let's go ahead and now write actually a mechanism so we can see how these three steps work. Again, keep it simple. Okay, that's what we are going to do. That has been my motto, although you have not been following my motto of keeping things simple. Okay, so here is the question. Write the mechanism of formation of chloromethane, of course, using chlorine and methane. Very typical question. I think this is what I have for you in the study sheet also. And let me just say I don't know if you noticed this or not, there is no homework for this chapter. I don't think there is one. It's just the study sheet, so you can kind of get an idea of how to write these reactions out. Okay, so write the mechanism of the formation of chloromethane using chlorine and methane. So we're going to write this. And again, remember, we have to do three steps, okay, in this case. So the first step is going to be initiation. And the initiation here, I cannot start with methane. I have to start with chlorine. So chlorine, and then I treat that with light and write the mechanism. So you get two chloride radicals. That's your initiation. There is no other initiation possible, okay, in this case. So if there is more things possible, I'll always tell you, okay, that they can do anything you want. But here you cannot do anything else. So now we go to propagation. And in propagation, you have a lot of steps to write. Sometimes there's 2 or 3 steps to write. Sometimes it's just 1, but a lot of times it's going to be at least 2 steps, okay, that you have to write. So the first one, generally, let's take methane. So I'm going to just go ahead and write this, okay, so that we don't have to write all the hydrogens out. I'm going to write just 1 hydrogen. And then this is going to react with Cl radical. This is the reaction I actually wrote in the propagation up here also, okay? But now I'm using chlorine, and now we're writing it a little bit in a more formal way, okay, of showing a mechanism. So in this case, now the hydrogen is going to break off. So now you have the carbon radical, and then you have HCl. Now, depending how you're feeling, like, do you feel like an organic chemist, or do you feel like not there yet, you know, kind of a thing? So like, you can just continue on here if you want to, because this is the product we are looking for, like, because this is propagation. In propagation, you're going to form radicals, okay? So you have to have that radical at least. The product, I mean, the HCl is a product, but it's not really our product. We don't need that, okay? We need something else. So then what you're going to do is get another molecule of chlorine. And please, you know, one thing I should mention to you, okay, about this, and I know you all have, you know, sometimes it always bothers you that, oh my God, you know, I don't know if I have another molecule that I can use. Of course you have like gazillion molecules to use, okay? So remember, 1 mole of any substance has 6.02 times 10 to the power 23 molecules. So even if you're using like a nanogram of a substance, you still have so many molecules to work with. And if you're thinking, okay, so I had chlorine in the initiation, but then I also formed the radicals. So do I have any chlorine left? Of course you have chlorine left. Okay, not everything is going to radicalize. So you still have radicals, you still have chlorine, you have methane, you have everything going on. Okay, now you can do things stepwise. Okay, what that means is you can take chlorine and give it light for, let's say, 10 minutes. Okay, you said, okay, for 10 minutes, I'm just going to shine light on the chlorine, make the radicals. Once I've made the radicals for 10 minutes, now I'm going to go ahead and add the methane, okay, to this reaction system. Once you add the methane, now the radicals are going to start reacting, which means that the radicals are going to start finishing, which means what? You're driving this reaction even more forward. Okay, so now the chlorine is going to become even more radicals, provided that you keep the light on. Okay, provided that you keep the energy on, you're still going to get more radicals. And you need that energy anyway, okay? To do this reaction, you need that amount of energy. So that definitely is going to be there, okay, until you're done with the reaction. So yeah, use whatever you want, okay? Just provided it's used logically, it's fine. So yes, you have chlorine, you have radicals, you have anything you want, any number of times, provided it's in the reaction mixture. Okay, so now what happens? This one breaks apart. This methyl radical is going to react with chlorine. So now what do you have? You have the CH3, Cl, and then you also have the chlorine radical. And because I'm writing propagation steps, I have to show the radicals, okay? I have to show these radicals because this is propagation. That's the main thing. And I form my product also. Okay, so I am all set. Technically speaking, I'm done with the reaction, but I'm not done with the mechanism. Okay, I have my product, but my mechanism is not done yet. Okay, so now after this, and what I meant by saying when I was trying to be kind of a little silly there, that how you're feeling like a, you know, organic chemist or not, I was going to say that if you want, you can write this reaction separately also. Okay, if you don't want to continue on there, you can continue on as a separate line. Okay, if you wish to. It's entirely up to you. I like to continue on because it saves me time and I don't want to keep writing the same thing again and again. Okay, so it's up to you how you want to do it. I would save time, you know. Okay, so now the last thing that I have to do is termination. So termination means what? Termination means that I have to finish off all my radicals. So what do? I get, what kind of radicals do you have there? If you want, you can write this, and I'm happy with this. If you want, you can write this, and I am happy with this. If you want, you can write this. And if you think I'm writing too fast, you will too. You will see once you get it, you're like, yeah, I got this. So I'm going to write or, okay, or, because you don't have to write all of these, okay? You can write any one of these reactions to show me that the reaction is terminated, okay? You don't have to write the termination of every single radical you formed. If you want to do it, that's a different thing, okay? In which case, the first two steps are sufficient. That's fine. Okay, but if you feel like writing the last one, that's fine too. But I need only one of these reactions. I don't need all of them, okay, from you. So just keep that in mind, okay? And sometimes when we waste time, it is because we, didn't pay attention to what we were supposed to write. Okay, so don't waste your time writing all the three. Just write any one of these reactions. The main thing is what? I don't have any radicals in the product. That is the main thing here. Okay, so question time. Anybody, any questions on any of this? All right. Again, when I do things, it looks, okay, like I can handle it, okay? But make sure you practice this and you write the mechanism, and then you'll see, okay, whether you get it or not. All right. Now, I have an issue. Of course, I have an issue. I always have issues. So here's my issue. Okay, I'm making chloromethane. Okay, so which means that I have CH3Cl, right? But what is preventing from CH3Cl to react with another chlorine radical and after a bunch of steps to get CH2Cl2? Can this happen, right? So I can repeat this kind of a mechanism and end up substituting another hydrogen to give me chloroform, another hydrogen to give me carbon tetrachloride. Can I do that? And yes, you can. Okay, which means what? It means that this is a reaction that has a lot of flaws. Okay, obviously this is not the best synthesis for chloromethane because you're not going to get one product. You're going to get more than one product. We are writing the mechanism only for one product, but you can get more than one product, okay, in there. And so it means that this reaction is not the best kind of a reaction to do. So when you choose to do free radical reactions, you can't just, randomly pick any reaction to do, because if you're not thinking it through, you're going to get a mixture of a lot of products, and then you'll be kind of banging your head like, how do I separate all of these things out? And then you also lower your yield, right, of what you really want to make. So this is not the best way to make it. This is just, we're writing a mechanism so we understand the mechanism, okay, of the reaction. But otherwise, yeah, nah, not very good, okay? But in some cases, these reactions work really good, okay? Which is where I'm going to take you, of course, because again, we can't do these reactions all the time. The radicals are extremely reactive. I mean, radicals don't get their name for nothing, okay? I mean, they are reactive. They will react with anything on site. Okay, so which means that once you have started a reaction, boy, you be ready to stop it. Okay, otherwise it's going to take its own turn and keep reacting, all right, until it's done. Okay, it's going to keep reacting. So you have to be very, very careful with free radical reactions. Okay, so what are the kind of reactions you can do? All right, so let's talk about halogenation, because this is what we did just now, right? Halogenation is what we did. So let's talk about halogenation, because this is the most common reaction possible using free radical reactions. And this is what you will be also doing. Okay, for most part, when I ask you to do any reactions for free radicals, it will be halogenation. Okay, so when I said when you start your reaction, you start with the halide, right? In the initiation step. In the initiation, you use chlorine or bromine. I asked you, or I kind of mentioned to you up here, let me go back here. So I said to you, we don't use fluorine, we don't use iodine, we use chlorine or bromine. And actually, even between chlorine and bromine, bromine is the better one. Chlorine is not so good. Okay, so why? Let's talk about that for a second, because that's where we're going now. Fluorine reacts really, really fast. Okay, which means that the bond breaks easily, and before you know it, fluorine is reacting, which means really hard to control. Okay, you don't want to work in a reaction which you cannot control. All right, so fluorine nobody's going to use. Okay, then next is chlorine. Okay, on the periodic table, that's how I'm going. All right, so chlorine is also very easy to break. It also reacts very fast. Okay, and in some cases it's really good, but in some cases it's just bad. Okay, so we don't use chlorine all the time. Bromine takes a little bit more time to break, which means that the bond energy is more. So which means it takes a little bit more energy to break it. So if it takes a little bit more energy to break it, you have time. Okay, you have time to think about things. Okay, the bromide radical that forms has time, all right, because it's not forming so quickly. So if it's not forming so quickly, it's a little bit slow. So now the reaction actually can take place a little bit better. Okay, so bromine is actually the best halogen to work with. Now, iodine is so slow, it is so slow, like you'll be waiting forever, okay, for anything to happen, for even the bond to break. It'll take days before the iodine bond breaks, okay, and we don't have that much time, right? So between chlorine and bromine, bromine is a better one, okay, to work with. Chlorine can be a good one depending on what you're making, okay, and what you're reacting. So I'm going to give you the differences between the two. So again, remember, fluorine and iodine are out, okay? You're not using those two at all. Okay, so let's talk halogenation. So let's see what happens, okay? So when you have chlorination, so if you just have ethane, for example, if you just have ethane and you want to do chlorination, now make sure that you write H nu or heat, okay, when you write free radical reactions, because if you just write CH3 and Cl2, this is actually a big fat NR, no reaction. Nothing is going to happen, nothing. Until you provide light or heat, nothing is going to happen, okay? So make sure you write the energy source, okay, to show free radical reaction, and that's how you'll see it from me also. Okay, I always show you that this is a free radical reaction by writing energy on there. So this one will give you CH3, CH2Cl. No problem, that's fine, it'll work. Okay, you can do this. Now you have to control this reaction, okay, before multiple substitutions start happening. You have to control the reaction, so you can either quench the reaction or you can add things a little bit slowly, so that way you can control the entry of the reactants and then the formation of the products. It depends what you're trying to make. Maybe this is not the best synthesis for it. Now if you have propane and you're trying to do the same reaction with chlorine, now, in this case, you can get two products because you'll get the chlorine here, and then you will also get chlorine, excuse me, I don't know why I'm writing bromine, chlorine on the end. So which means now your chances of getting constitutional isomers has just increased. This is a secondary halide, this is a primary halide. Remember, in the substitution reactions, we always started with a halide. Our substrate needs a leaving group, okay, either a chlorine or a bromine. We had hydroxide also, right? OH, the alcohol also as a leaving group, but that was only for acidic mechanisms. We could not use it for any of the normal nucleophilic substitutions. We had to turn the OH into a good leaving group. So how do you make those halides? This is how you would make them, okay? By using free radical reactions, you can actually take any alkane and convert it into an alkyl halide, all right? Your job is not going to be to worry about am I going to get multiple substitutions? That's not your job right now. Your job is just to use this in a synthesis step. Okay, that's it. So here, will you get 2 chlorines on any of the propanes? Sure. But if I ask you, write me all the mono-substituted products, then this is what you're going to get. Okay, so generally I will guide you as to what kind of product I'm looking for. Okay, so you also don't lose your mind in thinking like, oh my God, what am I supposed to give here? Okay, so I'll say give me mono-substituted halogenated, alkanes, or give me di-substituted ones. How many will you form? So, I'll give you something to focus on. Okay, so you're not kind of getting lost there. All right, so then let's see what happens with bromine, because this is with chlorine. Okay, so if you had something like this with bromine, you will still get 2 products. But now you actually have a major and a minor. These 2 are equal, pretty much. So when you do chlorination is wild. It's like, I don't care where I substitute. I will substitute everything, anything. But bromine is a little bit more picky. Okay, as I said, because it's a slow reaction, it works slowly. So it means that it will go to the carbon radical that is more stable. And which carbon radical is more stable here? It's a secondary one, okay, not a primary one. So you can see why we like doing bromination, okay, because bromination is a little bit better, okay, than chlorination. Chlorination is crazy. So now let's look at another one. Okay, so if you have something like this, and now you're doing bromination on this, I'll just use heat here just for the heck of it. So if you have ethyl cyclohexane, now what you're going to do is, if I ask you what is the major product, if I ask you what are all the products for this, all the mono-substituted products, we will write them all. But if I ask you what is the major product, the first thing you will do is you will identify all the carbons. Okay, sorry about the phone. Okay, so you'll identify all the carbons on here as primary, secondary, or tertiary, right? So you know that the ones I'm circling right now, these are all secondary. This one is primary. I'm leaving the tertiary one for the last. This is tertiary. So we've been doing this exercise ever since chapter 6, okay? Identifying primary, secondary, tertiary. Actually, even in chapter 2, I had you identify primary, secondary, tertiary. So you can see that we are using that a lot, okay? Here also. So what's the major product? Obviously, tertiary. I know that's what you're thinking. Sometimes I don't want to ask a question of you because I feel like you're going to think, oh my God, she keeps asking questions all the time, but it's my way of involving you. Okay, so this is it. This is the major product. Will you get other products? Of course you will. And let's write them all. Okay, so this is the major product though. So if you had to select one, this is it. But what else are we going to form? This is an exercise in constitutional isomers. So let's start here. I mean, I don't want to write them all, but you know what? I will do that just because I like you guys and I'm going to do this. And that's it. After that, if I go around more, I'll get the other one back. So technically speaking, I get 6 products, but one of them is the major one. And this is the nature of bromine. Okay, that bromine will give you at least some major products. Chlorine doesn't do any of that stuff. Chlorine is like happy, and it will just react with everything. Okay, that's in its site. Okay, bromine is a little bit more picky. So I kind of call this like love at first sight versus, love developing a little bit slowly, taking its time. And that's what bromine does, taking its time. So bromine is a little bit more selective. Okay, so you can write that somewhere if you want to. Oh my gosh, this is horrible handwriting. So let me write that again. Bromine is more selective. And that's because the bond breaks a little bit slower. Okay. All right. Now let's talk about stereochemistry, because that's what you were missing for so long. You're like, I have not talked about stereochemistry for a while. Okay, so what happens here? Let's say you have something like this. Yes, it's 2.5 mountains. And you're doing bromination. Again, with bromination, we're only going to write one product, the major product, the more stable radical that formed. Okay, so we know that the more stable radical is going to be the tertiary one. So this is where bromine is going to react. So now what happens is you actually generate a stereocenter, a chiral carbon. When you look at a radical, so if you have a radical here, this is hydrogen here, this is carbon, which means this is more like an AX3 kind of a geometry. AX3 means trigonal planar. So if it's trigonal planar, the bromine radical can come from either side, okay, because it's a plane. So it can come from either side. So if it does that, what you end up getting is a racemic mixture, just like you would get for a carbocation, okay? In SN2, we had inversion of stereochemistry. In SN1, we had a racemic mixture. So this is working like an SN1 because of the geometry of the radical. So you end up getting a racemic mixture at the end. Okay. The other thing I want to emphasize is break CH bond, not CC bond. Okay, so if I ask you for a substitution reaction on this, oops, traced everything there. On something like this, okay, if I ask you, okay, what's going to happen in this case, and if you give me this, then I know we got issues. And I know we have issues. I know we do, okay, because you tend to eat up your carbons, and I know you don't mean to, okay, but you have to count, okay, you have to count your carbons. You have to make sure that you write the right structure, okay? So what you really want to show me is this. This, okay, is the right product. I'm going to erase this, okay, because it's looking really ugly right now. There. What happened in the top one? In the top one, you ended up getting rid of this carbon. Okay, so usually, like, when I circle things for you, or when I put a question mark in your homeworks, that's mean that, I don't know what's going on here. Okay, because you're missing something. Sometimes I'll circle the carbon, like you're missing a carbon, things like that. And it's so normal for us to do that because we are working fast and we think, okay, we got this, but we don't got this. Okay, so we have to be careful and make sure that we count our carbons and make sure that our bond is the bond. Okay, so don't just add bromine, make sure that you actually form the bond, okay, there with the right carbon, and don't break the CC bond, okay, in there. That's an important thing. So then just a little bit about dye substitution. So you can get dye substitutions also, okay? It's not something that doesn't happen. It happens. So it depends on the question. If I ask you, give me all the dye substituted products, then yeah, just give me all the dye substituted products. Okay. So if I say, give me all the mono substituted products, then you just give me the mono substituted products. Okay. So in the mono, just one hydrogen is gone. In the dye, two. Okay. Two hydrogens will be gone. Now, where are they going from? It depends. So here we're going to write all the constitutional isomers again, because you can have bromine on these same carbon, or you can have bromine over here and over here. Again, don't forget this bond, okay? Don't forget this bond. Sometimes we just ended up, writing it on the carbon, but don't forget that, this is actually a carbon here. Don't lose that carbon. Okay, so what more? Let's say, so if you have a bromine here, you can also have a bromine here. I mean, you can draw all of them. I don't think I'm going to draw all of them here for this one, because dye substitution is a pain in the behind. You get so many different kind of isomers, so I'm just going to write etc. and you can just, write all of them. Okay, so you can move the bromines around. And so dye substitution is really, as I said, pain in the behind, because you get so many isomers, which means it's really not a very practical reaction to do. What's the point of doing this kind of a reaction where you're getting so many products? But it makes for a good multiple choice question. Okay, that's the only thing. All right, so I can ask you a question. Okay, how many different isomers are you going to get? Or I can write the products for you in a multiple choice question and say, are these all the products that you will get? So something like that. But otherwise, practically speaking, doing this in the lab or in industry is completely useless. Okay, it's not going to work. One thing I do want to talk about before I move on to the next thing is that if you do get isomers, okay, which we do, if you do get isomers, okay, like we're getting with chlorine and then bromine also, then how do you separate them? Okay, so the separation is also an important thing here. And I just want to mention it a little bit, okay, before I go on to the next thing, is the separation of isomers. And you have done this in the lab and you may not realize it, but this is actually a distillation thing, okay, because most of these compounds, they're liquids. If they're solids, they're harder to separate, okay, because crystallization is a little bit different than distillation. In distillation, you have different boiling points. So separating on the basis of boiling points is just a little bit easier, because not only you have distillation, you either have simple distillation or you have fractional distillation. Okay, so I may ask you this question: how do you separate these isomers? Okay, so you can separate them by distillation. That's one of the things. Okay, the other thing is, of course, the racemic mixture. So if you have chiral centers, how do you separate them? And those are done by resolution, which is really more like chiral chromatography. So you've done chromatography also in your lab. You must have done TLC. And TLC you do on a silica gel plate. A chiral chromatography is actually done on a column. Okay, so it's like a tube that you put the compounds in and then they separate out. Okay, so the separation of isomers, you have to do two different kinds of things. You can do distillation to separate the isomers, and then you can resolve them by chiral chromatography or something, in case you have a chiral center. Sometimes we don't have chiral centers, but if you do, then that's what you will have to use, okay, for separation. Okay, so I think this is a good time for us to take a 5-minute break, because what I'm going to do next for you is I have to do some very specific reactions that I really need you to focus on. So I want to give you a break now, so that when you come back in 5 minutes, you'll be all refreshed, okay, to listen to this part, because this is the one that's going to be synthetically very useful for you now and also next semester, okay, for organic too. So let's take a break. It's about 7:50 right now. So let's come back in 5 minutes, okay, 7:55. The only reaction we've done so far is substitution, okay, just taking an alkane and doing a substitution. So I just talked a little bit about all the different kinds of things that can happen, okay, when you're doing a substitution on an alkane. So first was just the mechanism, okay, taking you through all of that. Then all the other things that I've been talking about is just a little bit more like in depth, okay? So you can have multiple substitutions or you can have multiple products, but in the case of bromine, you have a little bit of an advantage and you will get only like one major product in there. Others will be minor, so it's a little bit more beneficial. Then you will also get a chiral center if it is possible that you're creating a radical that generates chirality, then yeah, you will have a racemic mixture in there. So all those things we're talking about. Then of course, side dye substitutions are possible also when you treat any kind of an alkane. As I said, control is really very hard, okay? In all of these reactions, the control is the main thing, okay? How do you control these reactions? Because radical reactions are very fast and they work really efficiently, okay? And that can be an advantage or a disadvantage also, okay? So we'll have to talk about both of those. So now what I want to do is I want to talk about some of the other reactions I mentioned, okay? So this was the first reaction, which is the substitution on alkanes. Okay, so now I want to talk about the substitution on alkene. And the substitution on alkene was actually the allylic substitution. I don't think this is the right spelling of substitution. There. So this is allylic substitution that I'm going to focus on. So here, let's say if you have an alkene like this, and you do bromination on this, you will end up getting this, which is an allylic substitution. How do we know it's allylic substitution? Well, 1, 2, 3. Start counting from the double bond. Okay, start counting from the double bond. 1, 2, 3. The third position is the allylic position. Okay. This is Br2. Okay, just bromine. All right, that's what we are working on right now. So instead of adding on to the alkene, like if I had given you a normal alkene, so if I said this and, do bromination like you did for me in the homework for alkynes, this is what you would get, is you would get bromine on 2 carbons, and this would be an anti-addition. This would be a normal reaction for you, but this is not normal. This is free radical reaction. Okay, so in a free radical reaction, you actually end up getting a substitution, and that too, allylic substitution. Okay, so no matter what you have, so for example, if I take something cyclic like this, and here is my double bond, and I add Br2 to this in presence of light, again, 1, 2, 3. All right, and I have 2 allylic carbons here. 1, 2, 3. So 1, 2, 3. I have 2 allylic positions here. So now I'm going to get a mixture. Okay, so I still have the double bond. That doesn't go anywhere. Then here I'm going to get a bromine, and then I'll get another product, and I will get bromination here. Obviously not a very good choice, okay, to do bromination on, because I don't want to get 2 products because both of them are equally stable. So it's not a very good one, okay? What a good one would be just simply cyclomethane. This would be fine, pentene, cyclopentene. So if I did this, now I will have only 1 product. So again, remember, count from the double bond, include the double bond, 1, 2, 3. So this is the allylic position. And that's your bromination. And that's it. That's the only product you will get. Even if you get it on the other side, it doesn't matter because you don't have any other substituent, okay, on there. So this is kind of what happens with bromination. You will see that I'm not writing anything with chlorine here. And actually, all the reactions we're going to do now, you cannot do with chlorine. Okay, you can only do this with bromine. You cannot do this with chlorine. All right, so do not change anything. You know, we like to change up things. Please don't, okay, because it will be wrong, okay, when you do that. Okay, so just a little bit about the mechanism. Just I want to cover micro mechanism over here so you understand how this is working. And this has to do with, of course, the mechanism, right? That's how this is going to work. So now if you react this with the bromine radical, this double bond will react with the radical, and you end up getting a radical here on this carbon. So that, and then you have the Br here. And just a second. I'm sorry. No, that's the wrong place. That's the wrong place because I have to start from the other side. Sorry. I have to start from here. Because I was thinking, I'm like, where did my resonance structure go? The resonance structure is going to form only now when I do the right thing. There. That's the radical that is formed. Now you can have resonance structures with this one. So there. And if you want to show the arrows, which is always a good idea to do that. So here is this, and then here is this. That's moving there. So the main thing is that the radical that's forming is very stable. And now all we need to do, the last step, is just join in. I know the arrows look really weird. Yours will too, I think. I'm not seeing your notes right now, but I'm sure yours do too. So that's all you will form. Okay, you will get substitution only on that carbon, on the allylic carbon, because of the resonance structure. Okay, that's the thing. So you don't need to remember the mechanism if you don't want to. Okay, I'll give you the reactions you need to remember. Okay, but the mechanism, I just wanted to show you that this is what happens. Okay, and this is the reason why you get allylic substitution instead of addition reaction. Okay, because generally in an alkene, you will end up adding on the bromine, right? As I wrote here in the box. Okay, this would be the traditional reaction that you would do on an alkene, but that's not happening in free radical. And that's why it's really important that you pay attention to the conditions of the reaction. Okay, so that was allylic substitution. Now we need to talk about addition. So in addition reaction, we're talking about, of course, alkenes. Okay, again. So generally what happens if you have this kind of an alkene and you add HBr to this, then you will end up getting, you know, Br right here, and the H is there, and that's Markovnikov addition. So we've done this. But if you take the same alkene and you treat it with HBr and light, sometimes we also write peroxides. Okay, so I'm going to show you that also. I'll write all the conditions. So when you see them, you're not confused, okay, as to what conditions are needed for these kind of reactions. So now in this case, you do get the addition reaction, but now the Br is here and the hydrogen is here. So this is anti-Markovnikov. So in the normal kind of a reaction, hydrogen will go to the carbon with more hydrogen, but in this case, the hydrogen is going to the carbon with less hydrogen. So something is going on, something is different, okay? And you'll remember we did some anti-Markovnikov addition back then also with hydroboration when we made alcohols, okay? So you can make alcohols in terms of, you know, a simple straight Markovnikov addition, and then you can also do them with anti-Markovnikov using hydroboration. So how does this one work? So in this case, of course, you're starting with HBr. So what you do, your initiation reaction, I'm not writing the entire mechanism. You will still start with bromine, but now your reaction mechanism is slightly different because once you have the radical, this one will start reacting. This is the mechanism I was writing before. Okay, so my bad. But now I'm not bad. Now I'm really good. Okay, so in this case, this will react, and now you'll form a tertiary radical here. So the Br is here, and the radical is here. This is the main thing, because this shows you that the radical that is more stable is the one that's going to form. The other radical would have been this, right? So if Br added here, then the radical would add here, right? So, but the radical doesn't form there because that's a primary radical, so this one will not form. Now we can add HBr, and now the hydrogen will add to the radical right here. And that's how you get the product. Again, if you don't remember the mechanism for this one, it's no big deal. I need you to remember the product that you will form. That's the main thing. So now if I were to take something like this, and I say, okay, I'm adding HBr with HNu, then, what you're going to write for me is that, okay, you still have the skeleton of the cyclopentane, okay, that is still there, but now you have to decide where you're going to put the hydrogen and where the Br goes, and you're going to put the hydrogen at the carbon with less hydrogen, so Br goes here, anti-Markovnikov. So this is very normal for bromination. I want to give you one more reagent that you can use for allylic substitution, because allylic substitution is extremely common because it gives you only a very specific product. So because of that, it's very, very common. Okay, so which means there are other reagents also. So I'm going to write in a different color some of the other reagent that is used, one other reagent, okay, that is used here, and that is called NBS, and that is N-bromo succinimide, and N-bromosuccinimide, this is 2 C's, okay, over here, this is 2 C's. It looks like this in case you see it in any quiz. And whenever you see NBS anywhere, that's a free radical mechanism. That's it. It will not give you anything else. Because sometimes when you use NBS, you will not see the light and the heat and all of that, okay? So I'm going to write some reactions here for you so you can see how the reactions are given to you in free radicals so you don't feel so lost, okay, in some cases, because free radicals are so different, that you end up kind of losing track of things, okay? So I'm going to write all the reactions. So a normal substitution is not going to happen, right? We wrote that already. So if you do something like this, no reaction. I should write no reaction. This is not forming. And I'll write the free radical on the right-hand side. Okay, so this is, oh, no, not happening. But with free radical, you can do this. So if you had Br2 with HNu or light, or we sometimes write peroxides. Those are the conditions you might see there. Then you will see substitution. Peroxides are also used as initiators. Okay, and sometimes that is why you see peroxides in there. They're very easy to break. Okay, so anyone who's ever bought any hydrogen peroxide from any pharmacy, you know that you have to keep it in a cool, dark place. They also sell it in a dark bottle. And so that's because it reacts very quickly with light. Okay, and if you leave it out in the warm temperatures, then it's gone. Okay, it's all converted into water. Okay, so you have to be careful with the peroxides. So this is one reaction. Okay, the other reaction we talked about was this one. So where here, if you do Br2, then you will end up getting something like this. But if you use Br2 with light, or you use NBS, then you get allylic substitution. I'm writing this. Make sure you write this in your own handwriting in a very nice way so you can actually remember these reactions, color code them, whatever you need to do. And then the last reaction is with HBr. So if you do this, then this is the normal reaction that you would have for an alkene, where the bromine is adding on to secondary carbon because that's how the mechanism works. But in the case of HBr with light or heat or peroxides, and I can use any of these conditions, and NBS I can't use everywhere. Okay, NBS is only for allylic. That's it. NBS only for allylic. That's it. Okay, so HBr in light, and now you end up getting this kind of an addition, which is anti-Markovnikov. So this is what we did today. Okay, pretty much we learned about these reactions on making halides. We learned the whole mechanism: initiation, propagation, termination. You know about the stability of radicals, the resonance that happens in radicals, okay, and the substitution and addition reactions. Okay, so the substitution reactions, there are two substitutions: the normal substitution on an alkane, and then allylic substitution. And the last one is addition reaction, which is anti-Markovnikov. So now we have choices. That's the thing. It's not about making your life more difficult, because now you have to remember this, but it's more about having choices that, okay, I don't want to get a Markovnikov product. That was the whole thing with the alcohols. Okay, so we can have many ways of making alcohols now. So the same thing here. Okay, so you have choices now to do a lot of things. Okay, any questions about any of this?
Professor, I have a quick question.
Go ahead.
I just want to clarify for NBS. You said it's for allylic only. Does it matter if it's like a cyclic compound or not?
It doesn't matter at all.
Oh, okay. Thank you.
Okay, any other question? All right. The chlorination is pretty much not specific at all. Okay, so chlorination, if you see chlorination anywhere, you will get multiple products. There is no major, there is no minor, so you will have multiple isomers, okay, in that one. So you will see that you will do a lot more bromination doing free radical. At this point, I will also give you chlorination because this is only your, the first time you're using this. But as we go on, okay, you will see that we use bromination a lot more because it's just a little bit more specific, in its products. Okay, I want to do two more things, okay, with you today. And the first thing I want to do is I want to talk a little bit about some practical aspects, okay? So if you want, you can keep your pens down and you can just listen, okay? Because this one, there's no exam question on this, but I want you to understand that all that you're learning for so long from me has practical uses, okay? And I've not been able to convey it in the last a few weeks because there was so much material. Okay, the last time I talked about anything practical, I think was, I don't know, back in maybe alkanes. We talked about, I think we did talk about octanes and whatnot. But alkenes have very practical uses. So I mentioned a few alkenes to you, like terpenes and, the wonderful aromas that you can get from alkenes. But I also want to talk about some other stuff, okay? And one of the other things I want to talk about is fats and oils. And fats and oils is something that we eat all the time, okay? Without fats and oils, there is no life, okay? Trust me, there's nothing like fried potato, okay, out there. So you need fats and oils in your life. Now, when you go, if you have ever gone for shopping and you go to the oil aisle and you want to buy oil, you see so many. Okay, it's like, I don't even know which one to pick. Should I take vegetable? Do I take canola? Do I take peanut? Do I take this, that, avocado? Oh my God, there are so many oils. Which one do I pick? Then there is the solid and the liquid oils. Okay, so there are two different kinds there. So then again, we have issues, okay, like which oil is good for you. So now let's talk about what oil is good for you. First of all, what is an oil? Oils are long chain fatty acids. Okay, and what are those? So you have long chains, and these are long chains like going up to C20. Okay, in some cases, they range from C16 to C20. All of them are even numbered, by the way. There's very rare that you will find any fatty acid that is odd numbered. Okay, almost everything is even number, and that has to do with a whole different thing. But anyhow, so fatty acids meaning fatty acid. Now, all of these fatty acids, they actually have double bonds in them. Some have double bonds, some have triple bonds. So it depends. Okay, people say, okay, olive oil is really good for you. Why do they say olive oil is good for you? Okay, and that is because it has a lot of double bonds in it. Okay, saturated fats would be without any double bonds in it, right? So you will have any kind of a saturated fat looking like this. Okay, what is saturated fat? No double bonds whatsoever. So what happens in saturated fats is when you have all of these molecules that get together, which they do get together, right? So, all these molecules are congregating. And remember that thing we learned about intermolecular forces? So those intermolecular forces start to play a role. Okay, so you do have the polar thing over here, of course, but here with these double bond or single bonds, excuse me, you have absolutely nothing, which means it's all non-polar, which means it's all van der Waals forces, which means over here, given the structure of this fatty acid, the next fatty acid will look like this once it stacks up. And here's the next one. Okay, so it's kind of like, shingles on the roof, right? So you just kind of, they stack up together like this. So what ends up happening is that you end up getting solids, okay, for the saturated fats. Because their intermolecular forces are a lot more. Why? Because they can get close together. Why? Because they're all the same kind of shape. Okay, so that's what happens. When you have double bonds, in double bonds, you have two kinds of double bonds. You have the trans double bond, which looks like this. I'm not writing the whole structure, just a little bit to show you the geometry of this. And then you also can have the cis double bond, which looks like this. Okay, so this is trans and this is cis. Now, you know that everybody will tell you, okay, anybody will tell you trans fatty acids are not good for you, okay? But try asking them why they are not good for you. And let's see if they can answer that, okay? Because you are learning organic and you're going to know this. So trans fatty acids are not good. Why? Again, because of their geometry, okay? So the next fatty acid that comes in is going to be like this also, which is just like the saturated fatty acid, right? So here you have trans, okay, coming in, and it is just like the saturated fatty acids. So trans fatty acids and the saturated fatty acids are very similar in their geometry. The cis fatty acids, on the other hand, they are a little bit different because their double bonds in is a little bit different, right? So the next fatty acid that comes along may actually look like this. So which means now there is so much distance between them. The next one may be like this, but then maybe the next one is the other way, right? So you don't have any control over that. How these molecules are aggregating, you don't know it. But the cis ones, their geometry is different, and because of that, they stack a little bit different, okay? So this is, first of all, the liquids and the solids, okay? So your solid fatty acids are the trans and the saturated fatty acids. Now, once you know that, okay, this one is a solid, this one is a liquid, now which one is good for you? So when we say, okay, olive oil is good for you, why is it good for you? Is because it has a lot of double bonds in it. Now, they don't know what kind of double bonds. I mean, you can find out. It's not that they don't know. Of course, everybody knows, okay, what kind of double bonds you have. But just the fact that it is a liquid tells you you have double bonds in it. When you have something solid, it means that the intermolecular forces are a lot. Okay, that's why something is a solid. Liquid means intermolecular forces are not that much. So for the liquids, okay, you're going to have definitely some double bonds in there. So generally they say that the olive oil, actually the kind of fats you have in there, have more cis double bonds in there. Okay, and so therefore it's better for you. Okay, fine, I understand, okay, that it's going to be better for me, but why is it better for me? Okay, so now we get deeper into like talking about why something is actually good. So between solid and liquid, liquid is better. In the liquids, you have all these different kinds, okay, and you can look up the properties, you can look up at the structure of all of these acids, they're all going to be out there, okay? So you can find out which, like peanut oil, vegetable oil, canola, avocado, whatever, all of these oils, their structures are all out there. Okay, so you can look at the structures. Okay, so they have cis bonds. Okay, cis bonds are going to be good for you, trans, not so good. Why? Why are they good for you? Why is cis double bond good for you? So now I want you to imagine yourself enjoying French fries, okay, which we all can do. And so if you're eating French fries, okay, and you're eating something that is fried in trans or something like a saturated fatty acid versus the cis, okay? So there are two different kinds of fries, or they can say fried in two different kinds of oils. Now imagine all of this oil going into your arteries. Okay, so your oil is going to be transported through, right? Your blood has to carry all of this from one place to another. Everything, by the way, gets processed in your liver. Okay, so everything has to go to the liver. So your oil is going happily to your liver through the blood. And what happens is when you have something that is stacked up like this, what is it going to do? It's going to cause a blockage, okay, in there. But if something is free flowing like this, where there is so much space in the middle, it's not going to cause a blockage. I think you know what I'm talking about now, okay? It's the difference in getting a heart attack versus not. Okay, so if your arteries are getting blocked, and what they remove from your arteries, if one has a heart attack and when you see, what's in those arteries, it's like white stuff just pasted on the arteries. That's called plaque, and it's there. You have to scrape it out, or cut it from there and say, okay, this is useless. You're going to have to put another one there, right? So they put stents and whatnot kind of things now. That's what's going on. Okay, so I hope you understand what fat is good for you and why it is good, because of the geometry of the cis versus the trans. Okay, that's one of the things about alkenes that you need to understand. Okay, now fats and oils have more things also in there, and it is related to what we just did with free radicals. So this is to do with cooking now. All right, so when you cook something, when you fry something, that oil that you have just used, now you can imagine what oil is, right? It's all of these alkenes that you're using and you're frying in there. And so what is happening? Well, reactions are going to start happening in there. Okay, the oil is not just going to sit there and fry and then just remain the same. That's not what happens. So oil is going to start reacting with the oxygen that is there. It's going to start reacting with other chemicals that you're putting it in there. Once that happens, then the bonds start breaking. Okay, so they start cleaving. And this especially happens in presence of oxygen. Okay, so there's a lot of oxidation going on. And you have already learned in alkenes that they have oxidative cleavage, right? So when you cleave the double bond, then now you end up getting acids and ketones and aldehydes and all of that. What does that mean? It means your fatty acid is no more fatty acid. Okay, Now it is chopped up into smaller pieces. That is generally not good for your body. Okay, and that's why we say that, once you've used the oil, you should not use it multiple times, because anytime you heat the oil to fry and then you cool it down and then you heat it again for the next time and then you cool it down and you heat it again, I mean, like, what are you doing to the poor oil? Okay, you're just killing the oil. And it happens, and we all do it, because who wants to throw the oil, right? I mean, it costs money to buy all this. So we end up frying in the same oil, sometimes 3 or 4 times. So you have to be careful. I'm not even telling you how much you need to fry. I'm just saying that this is what happens in there. Okay. So if you want to know what I do, I don't know. Sometimes I just look at the oil. Okay, so usually when you buy oil, it is a nice light colored oil, right? So it's very pretty, nice and clear and very light colored. Once it starts to darken up a little bit, then you know it's done. Okay, because at that point, the chemical nature is changing, all right, for the oil. So I leave it up to you to decide when your oil is good and when it's bad. Okay. Now, why do we need the fatty acids in our body? Okay, why do we need them? This is so much going on over here. Okay, this is so much. Why do you need fatty acids? You need the fatty acids because your cells are made up of a bilipid layer. Okay, so here's your beautiful cell, and that cell layer that you have here is actually a bilipid layer. Okay, so you have the lipid and then you have the acid, right? This is the polar part of it. So the polar part is in the water, and then here is the other side, and this is the water. So this is the inside of the cell, and we know we are made up of 70% water. So inside the cell you have a lot of water, outside the cell you have a lot of water. In between you have this bilipid layer. This bilipid layer is crazy, crazy, crazy good. It's got a lot of stuff, and a lot of stuff happens here. Molecules come in and out of the cell, oxygen goes in and out. I mean, so much stuff is happening at that cell wall. You want that cell wall to be good. So if you don't eat good fatty acid, your cell wall is not going to be good. Okay, you want that cell wall to be good. So, when they say you are what you eat, literally, it's correct. Okay, so if you eat good food, you will have good body structure also. Okay, so what happens now? Generally, this is still going to happen regardless of what kind of fatty acids you eat. Your body is still going to degrade, okay, because that's just the nature of life. Okay, but for example, if you look at your skin, okay, your skin is the biggest organ, and also your skin is the most exposed organ, okay, in your whole body. Your face is the most exposed, okay, of all the things. Your hands are exposed, okay, all the time. And this is something that you have learned to protect from the sun, right? So they always say, okay, you're going out in the sun, put some, sunblock, put some sunblock, SPF 30, SPF 50, that's what you need to put. So what are you doing that for? What you're doing it for is to prevent your cell wall from breaking down. How is it breaking down? Free radical reactions. Okay, so you have all of this oxygen that is out there in the atmosphere. You have all this radiation, like UV radiation, that is also in the atmosphere, that will start reacting with all these double bonds that you have in your bilipid layer, and it will break down. Okay, so it will break down. I mean, there's nothing you can do about it. Okay, so you can just protect it. So you can use the proper sunblock when you go out. You can see the people who work outdoors a lot, like gardeners and all, poor them. I mean, their skin is going to get damaged. Okay, and there's nothing they can do about it because they are so exposed to the sun all the time. So your skin is made up of bilipid layer. Okay, so you have to protect it. Okay, that way. So that's one of the things that happens with fatty acids and oils. Do you have any comment or anything you want to say? Any comment you want to make? That was a lot, wasn't it? Just about fats and oils. Okay, it's just lot of stuff going on. By the way, your skin organ is not the only one that gets damaged. The inside of your body, the cells get damaged in there too. Okay, and the way they get damaged is that it depends on the kinds of food you eat. So if you eat a lot of food that is processed, highly processed. It has a lot of chemicals in it. You know, chemicals, I shouldn't say chemicals as a chemist, you know, the chemicals you should not be eating. So a lot of processed food will have chemicals that are added to your food, which you really don't find in natural foods. Okay. So, you know, like frozen foods and things like that, there are lots of chemicals in there that you normally would not eat, you know. So if you eat those kind of chemicals, they react a little bit weird in your body. And one of the things they end up doing is then breaking up your cell wall, you know. And some of these chemicals, they will also start doing other reactions in there. And that's why there is a little bit of a higher rate of cancer that occurs. I'm sure there is everyone here, and I really hope there isn't, but all of us, I think, would know somebody who has cancer. Okay. And that's because, you know, of all the things that we are going around, and I'm not blaming anybody for eating wrong or right. And I'm not even saying it's because of that, because there could be genetic reasons. There are other reasons for getting cancer. But this is one of the things that can happen, because this did not happen 40 years ago, 50 years ago. Okay. We didn't have so much processed food, but now it's all around us. Okay. Not only that, we're also living in a very polluted environment, you know, so we have all these chemicals that we are exposed to. Just stand somewhere in downtown in the middle of the day, and you're going to smell all the exhaust fumes from the cars. You can't avoid it, you know. So you're smelling all of that stuff, all those gases, all of those chemicals are going inside your body. And once they get in there, they actually end up forming radicals because of the energy also that's outside. So when they form radicals, they start reacting. And one of the things they end up doing is chopping all of this. They also chop your DNA, you know, and so that's how mutations occur. So all of this stuff is happening. So how do you prevent that from happening inside your body? Outside, okay, fine, you can put sunblock, but inside your body, what you can do is you can eat your vitamins. Okay, so vitamins E and A and C, those are very good antioxidants. Okay, and you will see that that's what they're called, antioxidants. So you eat those antioxidants, and what these antioxidants do, they're like the terminators. Okay, so they're like the quenchers. They will go in there and they will eat up all of these radicals. All right, so make sure you eat your vitamins. Okay, and make sure you eat them in the quantity that is required, or eat good food. You know, I mean, whatever is available to you, you'd eat that. And remember, with eating supplements, you don't get all the supplement that it says on there. Okay, because a lot of it, your body doesn't absorb all of it. Okay, in there. So this was just a little spiel. Oh my God, it took me 20 minutes to talk about just fats and oils. Okay, and you can see there is a lot more in there that I'm not covering, okay, right now. But it's a very intricate, very key thing, okay, that I hope you can see how your chemistry is, you know, applied in all of these places. The second thing I want to talk about is radicals in the atmosphere. So I just mentioned to you that, you know, if you stand on the side of the road on a hot day, then, you know, you'll smell all sorts of stuff. And one of the things that you end up smelling and breathing in a lot is radicals. So where are those radicals forming from? And especially in a place like Florida, you know, which is really high heat and high energy there. So all these exhaust pipes, you know, from the cars, they're emitting all of these oxide, right? Nitrogen oxides, sulfur oxides. All of these will start doing all sorts of reactions, and then they form radicals in the atmosphere. So it's not really coming from you, it's coming from the cars. But of course, who made the cars? We did. Okay, who, you know, who has the exhaust? I mean, we do in general. So those radicals are there. The other places that radicals can form is also from what we call CFCs. And CFCs is chlorofluorocarbons. So that's exactly what they are. So they're like, you know, take methane and substitute the hydrogens with chlorine and fluorine. So chlorofluorocarbons have been used a lot in ACs. Okay, so AC and the fridge, so air conditioning, fridge, anything as a coolant. Okay, so all the coolants will have CFCs. Now CFCs are actually banned in America and some other countries also, because what CFCs were doing is that they were going up in the stratosphere and they were destroying the ozone layer. Okay, 20 years ago, there were 3 scientists who actually figured out the whole chemistry of the destruction of the ozone layer, and all had to do with radical chemistry. So all these CFCs, okay? So the CF bond or the CCl bond, this would break a lot more easily than the CH bond, okay? It has to do with bond energy. And then in the atmosphere, you have ozone, which actually does in equilibrium with oxygen, excuse me, O2 and O, okay, radical. So what the CFCs would do is they would push the equilibrium forward, okay? So there'll be no more ozone. And we need the ozone to protect our atmosphere, because the more ozone, the more the ozone is not there, the more ultraviolet radiation gets through. So the ozone is there to protect us from the ultraviolet radiation. Okay, so I don't know, whoever made this earth really thought this through, so otherwise who would make an ozone layer? But the ozone layer is there to protect us, okay, from the ultraviolet radiation. So what happened at one time, there were actually some holes in the ozone layer, and things started really getting heated up on the earth. And that's when the countries got together and came up with what's called the Montreal Protocol. And they decided, okay, we're not going to use CFCs. Okay, the problem here is, okay, fine, you don't use the CFCs, but there are a lot of other developing nations who have no other chemical to use except CFC as a coolant. So CFC is banned in some countries, but not banned in other countries, okay? And in case you're wondering, oh my God, my AC and my fridge, that can't be the only thing. No, but you're forgetting the supermarkets, you're forgetting all the stores that use AC. So, I mean, there's a lot of usage for CFCs, okay? So all of this stuff, this is all radical chemistry. And the last thing I want to mention here about the practical uses is in polymerization. And polymerization is an interesting thing. So polymerization is when you take something that is a monomer. So I'm going to take ethene, so CH2, CH2. And if you take N number, where N is more than 1,000, and then you do some reaction on it, and what you end up getting is a chain of that number of molecules. So you go from what is called a monomer to a polymer. So this reaction that is happening, it happens very easily, okay? But the only reason it happens is because of radical chemistry. So you initiate this reaction because you can see this is all carbon-hydrogen bonds, right? So it's not breaking by itself. So you do radical chemistry in order to form polymers. And if you're thinking, what do we use polymers for? Well, the one that I have written, this is the polythene bag. So this is polythene by itself, because this is ethene, right? This is ethene. So this one is polyethene, and the polythene is used a lot in the bags. So whether you go to Publix or Walmart or any of your big box stores, anyone you want to go to, anywhere where you see a plastic bag, that's a polythene bag, okay? Regarding whether the polythene bag is soft or hard, depends on the density of the material, okay? So the higher the density, the stronger it is, of course. The lower the density, the cheaper it is, the easier it is to break and all that. But essentially the basics is the same, okay? Which is that it's polythene. Then there are other stuffs also, okay? So for example, you can take something like this, which is tetrafluoroethene. And when you take N number of molecules of that, and then you polymerize this, then you get something which is called Teflon. And we all know Teflon one way or another because this is the nonstick. This kind of revolutionized the cooking, okay, for women. Well, I would say women because I think women were doing the cooking back then. I think we're still doing it. But in any case, so Teflon is the non-stick stuff. Okay, so all the non-stick cookware that came, that is because of the Teflon coating. So Teflon actually sticks very nicely to a metal, but it doesn't let anything else stick on it. Okay, so it was the non-stick material. It completely changed how you clean your dishes. So easy to clean, everything washes off, but it has its problems. Okay, so you can't use it at very high temperature, and it is actually toxic. Okay, so which means that if you're eating it, that's bad. So that's why they say if your cookware is scratched, you should not be cooking in it. Okay, because one scratch means that now you have a place where other breakages can happen, and so then you can start eating it, and so it's not a very good thing. So now, I mean, they have very different kinds of non-stick ware now, which is a little bit more durable than Teflon. But Teflon, that's how it got started. And actually, Teflon is such a non-stick thing that you have used Teflon in the lab also. You might remember in your separatory funnels or in the burettes, you will see those plastic things. That's not plastic, that's Teflon. Okay, so it's very good and it doesn't stick to anything. People also put Teflon coating on pants, and I'm really literally talking pants over here. So like if you have khakis or something and you put Teflon coating on it, then you can spill whatever you want on it, nothing, it'll not stain it. So that's a nice little advantage, of Teflon. The other thing here is this chemical. I'm just giving you examples so you understand how important all of this is, for us. So this molecule that I have drawn, this is called styrene. You probably know where I'm going with this now, because the polymers are very similar to their names. Okay, so this one now you will form what is called polystyrene. And polystyrene, is the takeout boxes. All of the takeout boxes from any store, those are all polystyrene. Okay, if you're having a picnic, you get a stack of plates, you can get paper plates or you can get the polystyrene plates. Polystyrene is extremely good because it's such a good insulator, so I mean, you can't imagine having a coffee in a paper cup, so coffee is really good in a polystyrene because it's such a good insulator. Your coffee will stay hot for a longer time. Okay, so advantages, disadvantage, it will never degrade. That's it. So environmentally, it's the worst stuff possible. All of the polymers I have written so far, by the way, they're all super bad for the environment. They're all really bad because none of them degrade. Okay, so plastics are going to be here forever. The plastic bags, that's why people are trying to get out of plastic bags. Some countries have completely banned them. I mean, either you have to pay to get a plastic bag or something like that. But all of these things, they're environmentally terrible. So chemists keep working, and biologists also, they keep working on figuring out either some biodegradable polymers or things that are recyclable. So, or carry your own cup, carry your own bag. I mean, like a lot of people used to carry their own bags, so what's wrong with that? So people are carrying their own bags now. So things like that, so, but this is also a free radical gift, in the sense that these reactions would not happen if it was not for free radicals. Okay, so all of this stuff, this is all part of our life, and this is all part of free radical chemistry also, okay, in some ways. Any question, any comment, or did I put you all to sleep? I put you all to sleep. Okay, all right, then I can continue talking, and hopefully you will listen to the recording later on. So the last thing I want to do today is some synthesis, okay, because you know that everything that we learn translate into some sort of synthesis, okay? And I will always give you some synthesis to do one way or another in your exam. So here is one, okay? So let's talk about synthesis. And I'm going to use free radicals in this synthesis. So if I ask you to make something like this. So here you have a cyclopentane, and I'm asking you to make an ether. And you're looking at this and you're probably thinking, I don't know where to start. So let me show you how you can start, okay? You can start by looking at the product, and you can say, okay, I can see oxygen. So which means that I can do some sort of a nucleophilic substitution, okay, on this. So which means that I need a substrate and I need a nucleophile. Remember, you only know a few reactions. You don't really know a whole lot more. And if you give me something that I have not covered in the class, that's zero, completely zero. Okay, it doesn't work. So don't ask anybody else, okay? Because I will know, okay, whether it's yours or somebody else's. And sometimes all of you have the same synthesis. So, you know, I don't know. You collaborate, that's fine too, I guess. Anyhow, so you need a substrate and you need a nucleophile. So now what's your nucleophile? Your nucleophile is something that is negatively charged, right? That's why I always write Nu minus. So your nucleophile, you know, is something like this. This will work, right? That's a good nucleophile. That's ethoxide. So you've used this like a gazillion times. You can also use this as your nucleophile. So what I'm doing is I'm just fragmenting this, okay? That's all I'm doing. Okay, fine. That's my nucleophile, which means that I need a substrate. What does a substrate have? A substrate has a leaving group. What's a leaving group? A leaving group is something like a bromine or a chlorine. Remember, you're not going to use OH because OH is not a good leaving group, especially when you're doing SN1, SN2. So, which means if I choose this to be my nucleophile, then my substrate has to be something like this. If my nucleophile is a cyclopentane with the oxide on it, then the other part of it, which is CH3, CH2, CH3, this has to have a leaving group. So that's my substrate or that's my substrate. So now we're looking at the reaction that we are given right now. It's taking us so long because this is the first time, okay? Hopefully, as you get comfortable, it's not going to take you so long. So now you're looking at your starting material, which is cyclopentane. So you're like, okay, from cyclopentane, I think this one would be easier to make because you just learned free radical reactions. And if you do this, you can easily do a substitution reaction and get a bromine on the carbon. And then all you need to do is get an ethoxide and do a substitution reaction. And if you're thinking, oh my God, that was so easy, yes, it is. As I said, you only have limited reactions that you can work with, okay? So I can't give you too complicated. All the synthesis you will do at this point, 3 steps maximum or 4 steps, 4 steps maximum. That's it. Okay, it's not going to be longer than that. If you're making it longer than 4 steps, I know you're lost. Okay, at that point, I know you've either talked to somebody who doesn't know what they're talking about, or you're just lost and you're just like, just trying to find your way. Okay, because all the synthesis I give you, maximum 4 steps. That's it. I can't give you anything complicated right now. So this is it. Okay, this is how you would do it. And so here is your free radical reaction, okay? And this one was SN2, so this one is free radical. So all these reactions, you know, now what we're doing is we're just putting them together, okay, in a little bit larger synthesis. Okay, let's do another one. And in this case, let's say I ask you, and again, remember these reactions I told you, I can be creative, but these reactions are coming from the Klein textbook. So if you have the Klein textbook, you will see all these reactions in there. He has a whole chapter on synthesis. So if you have the textbook, please use it. Okay, yeah, there's one complete chapter on just doing synthesis of molecules. So just look through that, admire it, learn from it. Okay, so again, we have OMe. So again, we have an ether. Okay, again, whenever you see an ether, think SN2. Okay, very easy. So think SN2 reaction, which means that you need a substrate and you need a nucleophile. Okay, so that's something that you need. So we can do whatever we want, okay, over here. So again, our nucleophile can be this, and our substrate can be methyl bromide. which is really CH3Br. CH3Br is a really good substrate because it's a primary substrate, and then we will definitely get only SN2 reaction. Okay, which is kind of similar to the top reaction also, because I mean, there's not much side products going on. Okay, because sometimes, you can have issues like a bulky nucleophile, not enough nucleophile, whatever. But the top reaction, not that many issues. So same here also. Methyl bromide is really a good substrate. Okay, you will never have many issues, which means I need to figure out how to make this now. The double bond is still there. Double bond has not gone. So if the double bond is not gone, it means nothing is happening on there. And the carbon that I'm working on right now, you can see it is 1, 2, 3. So that's the allylic carbon. So as soon as you think allylic, you're like, oh, yes, I can use NBS, because NBS is going to give me allylic substitution there. Now, can you just go ahead and use methoxide over here, okay, to do the substitution? You can, if you wanted to, because here you have a substrate already. Okay, so if you want, I'm going to show you two syntheses, okay? So this one here, if you just use methoxide right here, you can go ahead and do the substitution right here, SN2, and we're done. But there is another way to do this, which is just a little bit longer, okay? And so it depends on if you're lost or not. I don't know. I wrote this one out because maybe I was just having fun writing a synthesis. I don't know. But this is what I chose to do. So this one will give me OH. So this is still SN2. And now I'm going to go ahead and make my alkoxide. So I'll just treat this with Na. This is the reaction I gave to you in your homework. So now my nucleophile is ready. And then all I need now is CH3MgBr. I'm sorry, CH3Br. Well, I don't know where the Mg came from. CH3Br, and now you get the SN2, and that's fine. OMe. You will see that most of my syntheses are going to be like 5 points synthesis. So with 5 point synthesis, sometimes I make it 7 points just so I can give you more credit, but not because it's 7 steps long. No, usually I have like 1 point per step, and so, or 1 point for a reagent. And so most of the syntheses are like 5 points. So that way, if one of your reagent is wrong, I take off 1 point and things like that. So, and again, if it's 7 points, it means it's 2 points per step. That's all it means. It doesn't mean there are 7 steps to it. Okay, so don't make your synthesis too long. So this is just kind of how you can use free radicals. Okay, so again, this was the free radical right here. And you can see that I did not use light or heat with it because NBS implies that it is free radical. Okay, so you don't have to use light or heat here. Okay, and there are going to be more synthesis online also if you want to check. And if you want me to do more, and I can just make a video, okay? Because right now it's not going to make any sense. Because the more you remember your reagents, as I said, the better you feel about doing synthesis. Okay, so I can do many syntheses right now, but unless you do them yourself, it's not going to make any sense. Okay, so do some synthesis yourself from Klein. I can throw in some molecules also if you want. So let me work on that, and maybe this weekend I will upload some challenges up for you so you can do some synthesis also and practice on it. But that's about it. That is the end of Organic 1, believe it or not. I think you want to believe it because, yeah, it's been too long, right? It's been going on and on.